Good morning, students. So in the last class we discussed in detail about the total angular momentum, so which was represented as capital J, so which is equivalent to addition of orbital angular momentum and spin angular momentum. So capital J equals capital L plus capital S, and all are vector quantities, so very important one. Okay, so they show the magnitude as well as the directions. So we know about those quantities are vector quantities. And of course we started with orbital angular momentum earlier, L. So L is an has a magnitude as well as direction. It's a vector quantity, and we are going to add with S, L with S. So S is a spin angular momentum. So spin also is a vector quantity. Correct. So it has a direction as well it has a magnitude. So J plus L. Only then we can add. Only vector quantities can be added. Correct. Only vector quantities can be added. If L is a vector quantity, S must be a vector quantity. No other way. So J equals L plus S. Not only the magnitude, but also its components also should be added. Like Jx equal to Lx plus Sx, and Jy equals Ly plus Sy, and Jz equals Ly plus Lz plus Sz. So we know already about this. So S is a vector quantity, and it represents the spin angular momentum, and small s represents a magnetic moment. Okay, magnetic quantum number. Capital S stands for spin angular momentum. Small s stands for spin quantum number. Okay, so especially for electrons we know already plus half and minus half. So these are the things that we know already. But in history, how it arose? So it started in the year 1920. So when the spectra of alkali atoms, something like sodium, potassium, cesium, they observed the spectral lines, and with the help of some high resolving spectrometers, they observed, and they were observed as doublets, not single lines. And with the naked eye, we can find out only single line, or with less resolving power of spectrometer, so we can have only a single line. Suppose if we use high resolving power of a spectrometer, then we could find out some double lines. It was so surprised for them, and it could not be explained on the basis of orbital angular momentum. And we know already about, at the time, 1920s, 1910, 1920s, orbital quantum number and principal quantum number existed. Okay, so it could not be explained on the basis of orbital quantum numbers. And people thought, especially Bohr and Sommerfeld, they thought that some shells, and this will have some inner shells. See, inner cell, there exists some inner cells in the fine structure of spectra, so which is especially doublets, multiplets. So what we call this as fine structure of spectra. So it was considered first by Sommerfeld, and he introduced an inner quantum number to distinguish the various states of multiplets. He suggested the property of electron having some inner cells, okay, core electrons. The explanation of the doublet structure of alkali atom, so is explained by the concept of electron spin, which we are going to see now. And in the year after 2 years, in the year 1922, Stern and Gerlach, they showed the spin is quantized. Okay, of course, spin will have, just now we said, this is about plus half and minus half. Only two values it has. So two values means it must be quantized. It's a discrete one, either plus 2, plus 1 by 2 or minus 1 by 2. Okay, actually speaking, we should say this is about h bar by 2 and minus h bar by 2. But generally we will say that this is plus half and minus half. Okay, we are going to see in detail. Okay, Stern and Gerlach experiment. So in the year 1922, Stern was from Poland. He was a Jewish family. He was a Jew, and he was a theoretician, and he studied chemistry. Especially he was so interested in physical chemistry. So in Poland he obtained his PhD in physical chemistry. At the time, 1910s and 1920s, Albert Einstein gave lot of lectures in and around the universities and the research institutions. So he was so interested in attending Stern. He was so interested in attending his lectures. So he used to go wherever Albert Einstein gives some lectures. So out of this own interest, and he could get a lot of inspiration about Albert Einstein's lectures, and he could learn the fundamentals of quantum mechanics. So Stern learned all basic concepts of quantum mechanics from Albert Einstein. So he was so interested. So later he wanted to get a job in the University of Frankfurt, Germany. So he went there in 1921. So at the time he had an idea. He had an idea about the orbital angular momentum. Earlier in the year 1911, Niels Bohr predicted one concept about orbital angular momentum. So we know that electrons revolve around the nucleus, we know already. It has an orbital angular momentum, we know already. Suppose we are going to keep this atom in the magnetic field, and this orbital angular momentum will be quantized. In the sense, this has a direction as well this will have a magnitude. So direction of the angular momentum will be quantized. So this was the prediction done by Niels Bohr. I repeat, Niels Bohr predicted that if you are going to keep the atom in the presence of magnetic field, the orbital angular momentum of the electron, the direction of the orbital angular momentum of the electron is quantized. Okay, so this was a prediction done by Niels Bohr. Stern wanted to prove this one. He had an idea about how to prove this idea. That is, the direction of the orbital angular momentum of the electron is quantized. Okay, direction. So at the time he met his own friend Gerlach. Gerlach from Germany. He also studied in University of Frankfurt, Germany. So both met each other and they shared their ideas. So in the year 1922, Stern insisted this experiment to Gerlach, and Gerlach had a small apparatus. Gerlach had an apparatus, and Gerlach actually wanted to discover something new of dipole moments of the atom. So he wanted to test whether atom has a dipole moment or not. The magnetic moment of atom, it was put forth by Gerlach. So Stern and Gerlach, they worked together exactly 101 or 2 years before. So 1922. I think on 7th February. So 1922. So at the time, so Stern insisted this idea to Gerlach, and Gerlach, as I said, Gerlach had an apparatus, and Stern wanted to go for an interview. So he went to University of Frankfurt for the interview. So Gerlach overnight he did the experiment. Overnight. So the experiment goes like this. The experiment is like this, exactly like this. And they took silver atoms. The silver atom was vaporized. More than 1000 degrees, the silver atom would be vaporized. Okay, so we know already. So the vaporized silver atoms is sent through the small slit. The slit was a rectangular shape. In fact, Gerlach used first time rectangular slit. He could not get the intensity properly. So immediately he made the slit as a round one, circular one. Immediately he got the result as very perfect. The intensity was very clear. So he used the slit as a circular one, circular aperture. So he sent the vaporized silver atom through the slit, okay, and through the magnetic field. Okay, this was overnight done exactly on February 7th, 1922, 1 or 2 years before. Okay, 1 or 2 years ago. And they thought they guessed. We know already that silver atom has 47 protons, 47 electrons. Of course, 47 electrons means 47 protons. So they are all neutral in charge. So silver atom as a whole, it's a neutral one. Suppose if it is neutral, if it passes through the magnetic field, he guessed that he could obtain only the spot at the center, because this will not be deflected by the magnetic field. Correct? You have a silver atom, which is neutral atom, which is passed through the magnetic field. Magnetic field will never deflect the neutral atom. Correct? So in the sense that he thought that it could exactly impinge, it could exactly go exactly onto the center, okay, at the center, because there will be no deflection at all. Okay, he guessed. Then one more thing is, they used only non-uniform magnetic field. Suppose if they use magnetic field, uniform magnetic field, okay, what will happen? The forces of dipoles will cancel with each other. Again, the silver atoms will go straightly into the at the center. So they used only non-uniform magnetic field, okay, so that the forces of dipole will not cancel with each other. So they guessed that neutral atoms, okay, it has to go exactly at the center. Instead, they looked at the screen. Half of the beams exactly they reached the top, half of the beam reached at the bottom. Okay, just imagine that you have a silver atom which are neutral and they pass through the magnetic field, and exactly they go and sit at the center. They guessed, but on contrary, they could observe half of the electrons they went to the top one, half of the electrons exactly they reached at the bottom. So it was a concept, spin up and spin down. Okay, they didn't say anything, think about spin at the time at all. Spin concept could not be explained at the time. Now you guess classically. So now we'll have a silver atom. Okay, silver atom has 47 electrons, 47 protons. You just guess. And they guessed it should have been done by means of orbital angular momentum of the electron. They guessed. See, silver atom was a neutral one, but now it has been deflected, either side, up and down. If it is pakka neutral, they guessed that it should be exactly, should not be deflected. Correct? It should go only at the center, but now it has been deflected now. So they guessed that silver atom has an orbital angular momentum. So the deflection would have come only by means of orbital angular momentum. So just now they checked the number of electrons, 47 electrons. Out of 47 electrons, inner cells, K, L, M, N, O. Okay, inner cells will have 2, 8, 18, 18 plus 1. Okay, so out of 47 electrons, 2, 8, 18, 18. So we have 46 electrons. Remaining one is left out. This last one is nothing but the 5s1 electron. Okay, 5s1 electron. So they guessed that this magnetic moment, okay, magnetic moment should have arisen only because of this orbital angular momentum. The deflection would have taken by means of orbital angular momentum. They guessed. And they guessed even the 5s1 electron has the orbital angular momentum L/1. They guessed. After that, they realized that 5s1 electron has no orbital angular momentum. See, 5s1 electron, there is no angular momentum at all. If there is angular momentum, of course it should have done. There will be some deflection, correct? So, for example, you have a charged particle which revolves around the nucleus. You are going to apply the magnetic field. The moment when you are going to apply the magnetic field, due to the existence of magnet, due to the orbital angular momentum, it has to go either that side, or this side, or this side. Everywhere it has to go, according to the classical concepts. But it has gone only up and down. You have spin up and spin down, something like that. So they checked about 5 years in electron. So at the time that they concluded that L was equal, there was no angular momentum at all. L equals 0. So for 5 years, 1 electron, L equals 0. So there is no orbital angular momentum. So again they guessed that how it is possible that uh, the the magnetic property would have been acquired. So they guessed that some intrinsic property of the electron will be there. Some property will be there. Some intrinsic property. This intrinsic property, they guess that this is spin. So spin is an intrinsic property. Okay. So it has built-in. So every electron has a spin property. It's a built-in property, intrinsic property. Either it can be, the spin can be up or down. Okay, it's a linear combination of up and down. You have an electron, we cannot guess whether the electron has two states, which one is up and down, we do not know. It has a linear combination of spin up and spin down. Okay, you have to remember, the moment when you are going to measure, the moment when you are going to apply the magnetic field, only then this will show spin up or spin down. Okay, for example, if you have an electron like this, okay, suppose to consider this is an electron. So the spin up component is somewhere like this. Then you are going to apply the magnetic field, and this spin up component exactly will pass through the magnetic field and it will go up. Suppose if you have a spin component is exactly like this, you have a magnetic field, okay, through which the electron passes. Then immediately this will go into down, okay, spin down. So half of the electrons will go into up, half the electrons will come into down. So spin up and spin down. So electron has both the states before the measurement. So this is superposition of states, linear combination of states, spin up and spin down. The moment when you are going to measure, this will show either spin up or spin down. So that's why it has come as half, exactly like tossing the coin. So before tossing the coin, we will not be knowing whether head or tail. We do not know. It's a linear combination of in the coin. It's a linear combination of head and tail. Correct. The moment when you are going to toss the coin, after that only you will realize that whether it is head or tail. Okay. So this is exactly same thing. Okay. So spin is a property. It's intrinsic property, built-in property for the electron. Each electron will have spin property. So this will have both the states, either up state as well down state. Both the components it will have. The moment when you are going to measure, only then this will show spin up and spin down. Now coming to the point, very important point, is electron really spins or not? Of course, we know that suppose the electron revolves around the nucleus. Okay, any charged particle which revolves around the nucleus will produce a magnet. So magnetic field will be exactly like this. Suppose electron revolves around the nucleus like this, the magnetic moment will be exactly up. Okay, this has a magnet. This will acquire a magnetic field. Suppose the electron revolves around the nucleus like this, the direction of the magnetic field will be down. Okay, any charged particle, if it revolves around the nucleus, this will produce magnetic field. So this is about orbital angular momentum. But according to this silver atom, L equals 0. Okay, L equals 0. So there is no magnetic field at all for L equals 0. Okay, so this spin up and spin down would have arisen by means of the spin of the electron. Okay, suppose the electron spins like this, for example. What of the magnetic direction? It will be like this. The spin, if it spins like this, again the magnetic field will be in this direction. Okay. Now, actually speaking, electron is not a particle. Electron is associated with the wave. Correct. Electron is not a particle as like a solid object. It is an extended object. It is like exactly like associated with the wave. So electron will not spin. It's a very, very important concept in quantum mechanics. The electron will not, but it has an inherent property, intrinsic property, built-in property. It has come from mathematical point it has come, that is h bar by 2 and minus h bar by 2, both the values have come only from mathematical idea. Okay, actually speaking, electrons will not spin this much speed. It's an intrinsic property, inherent property. Okay, so Stern, at the end, Stern and Gerlach, they pointed out that they will have only two directions, spin up and spin down. Classically speaking, suppose if it spins exactly like a top, if it spins, so see, for example, if it spins like this, it will spin here like this also. Classically speaking, it has spin. So in all the directions, we will have a magnetic field, correct? Classically speaking, but we have only up and down. Okay, 50% that side and 50% down. So only possibility is that electron will have only two components, spin up and spin down. That's all. That is the n. Okay. So Stern and Gerlach in the year 1922 they published a paper, and immediately Gerlach, at the time Stern was not there, correct? Stern was attending an interview. So Gerlach gave a telegram to Niels Bohr that your idea, which you predicted, has become true. Because he predicted that the direction of the orbital angular momentum of the electron is quantized. So now it is quantized. One is up, another one is down. So both the directions are there, only quantized, not any other directions. So Gerlach immediately gave the telegram to Niels Bohr. In the very next year, Albert Einstein nominated for Nobel Prize, both of them, Stern and Gerlach. They did not get Nobel Prize because the proper explanation was not done. Okay, after 4 years only, Uhlenbeck and Goldsmith, they gave the idea about the vector atom model, the space quantization, the direction is quantized. After that only it came. This Stern Gerlach experiment came very fast. It became very popular. Okay, so after that, in 1933, Stern continuously was doing some experiment. Especially he did some experiment on the dipole moment of a proton. After 10 years, he got the Nobel Prize for the discovery of dipole moment of the proton, 1943, Stern alone. But Gerlach, Stern, of course, the second most nominated person, 82 times between 1925 and 1943. So nearly 82 times he was nominated. So at the end he got the Nobel Prize. Gerlach did not get Nobel Prize. Okay, so that's the story. And of course, the spin up and spin down arised only because of the unpaired electron. That is 47th electron. Okay, only one unpaired. All the other things are paired electrons. Okay. So this was evidence for the space quantization of angular momentum. As I said, after 4 years, 1922, the experiment was carried out, okay, by Stern and Gerlach. But in 1926, after 26, Uhlenbeck and Goldsmith, they were the students of Paul Ehrenfest, okay, Paul Ehrenfest students. Uhlenbeck and Goldsmith suggested that the electron has an additional property other than orbital angular momentum, okay, additional property, which is nothing but inherent property, built-in property, intrinsic spin angular momentum, ms. So spin is a property of an elementary particle such as protons, neutrons, electrons. Okay, spin is a vector quantity which we discussed earlier with a dimension of angular momentum. Okay, J equals L plus S. What are the units for L? The same unit for S also. That will be the unit for J also. Okay, so the classical analogy is the angular momentum of the top, as I said, rotating rigid body. Okay, actually electron will not have particular spin. Okay, it's a mathematical entity. The characteristics values of components of the spin are h bar by 2 and minus h bar by 2. So it was found out by Paul Dirac in the year 1927. Actually, in the year 1926, Schrödinger, he applied his own theory, Schrödinger wave equation, quantum theory, in special theory of relativity. He tried. and he could not obtain the proper results. So Paul Dirac used the Hamiltonian, Dirac Hamiltonian. At the end, he could obtain these two values, h bar by 2 and minus h bar by 2, okay, for the electron. So the spin concept, it was very strongly proved. The spin is measured in the unit of h bar. The characteristics values are plus of and minus of. One is up, another one is down. It is termed as quantum numbers s equals 1 by 2, and of course it has two values, s plus or minus 1 by 2. It is associated with the component capital S, spin angular momentum, in a fixed direction. This direction is the direction of the applied magnetic field. The experimental evidence of existence of electron spin was given by Stern and Gerlach, 1922. Okay, and of course we have already seen this figure. The figure is exactly like this. The first experimental evidence for space quantization in a magnetic field. Okay. Okay, and this was the pattern obtained by Stern and Gerlach in the year 1922. So I took it from internet. So thanks to internet, okay, I should say with acknowledgement. So this was taken by Stern and Gerlach in the year 1922. See, look at the picture now without the application of magnetic field. The moment when you are going to apply the magnetic field, so there's a split. See, there's a split up and down. Suppose we are going to apply magnetic field like this. Again, the split will be exactly like this. We are going to apply magnetic field like this, the split will be like this. So it depends on the direction. See, again when you are going to switch off the magnetic field, it will become exactly like this. See, like a line. So that's a split. See, up and down, left and right. Okay. So it was inferred that the deflection was due to two groups of atoms, that is due to one group of atoms in which the valence electron, okay, magnetic moment was aligned along the field, and the second group in which the magnetic moment was opposite to the magnetic field. So this was done, we have seen already. The magnetic dipole strength is given by E h bar divided by 2mc. The contribution due to the orbital angular momentum is 0 because pi s electron has no orbital angular momentum, so L equals 0, and the deflection was due to only single electron spin motion. Okay, thus the spin angular momentum of the electron is equal to h bar by 2 and minus h bar by 2. So this is for the spin contribution, and this is for the magnetic moment of orbital angular momentum. For the spin magnetic moment, mu s equals minus E divided by 2 m naught c 2s. Okay, 2s. So one is up, another one is down. So that's why this 2s exists, two numbers. And this is for the orbital angular momentum. Okay, orbital angular momentum. So orbital magnetic moment mu L is given by minus E divided by 2 m naught c L. Okay, so this also will arise magnetic moment. This also will arise. Orbital angular momentum also will arise magnetic moment. Spin also will arise spin magnetic moment. Okay, the contribution from both. So that's why we have added these two to get a total angular momentum J. Okay, J equals L plus S. So as we discussed earlier, that spin is a vector quantity. Okay, so spin is a vector quantity. Dimension exactly is equivalent to angular momentum. So since spin is a vector quantity, its magnitude is given by this expression, S into S plus 1 h bar square, and its direction is given by ms h bar. Okay, so this is for the direction and this is for the magnitude. So ms equals minus s to plus s. Okay, so minus s, s plus 1, minus s plus 2, dot 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 s. So minus s to plus s. It has components sx, sy, sz, it has components. Okay, so of course we'll have to remember the Pauli's exclusion principle also. Okay, so we'll have to remember Pauli's exclusion principle. So here, so that's why Pauli has gone for only 2 by 2 matrix. So that we are going to see later. So spin has no 3 directions, it has only 2 directions. So spin up and spin down. So that's why 2 by 2 matrix will exist. In the relativity, of course, we'll be dealing with 4 by 4 matrix. That we'll see later. So thus it brings out the concept of space quantization of angular momentum. So as we said, spin is quantized. So spin is a vector quantity. So that's all. So in this class we learnt about the story of Stern-Gerlach experiment thoroughly. Then spin is a vector quantity. It has a magnitude as well it has a direction. It's a mathematical beauty. So it's an impact. It's a feeling that we can have. Okay. So spin cannot be observed like a top, like a classical particle. Electron has no spin, but its inherent property. Electron will not spin. Okay, so very important thing. Electron will not spin, even though if it spins, it has to spin with a velocity more than the velocity of light, which is not possible. So electron has inherent property, intrinsic property, built-in property. That intrinsic property is nothing but spin magnetic moment. Okay, it has a magnitude as well it has a direction. Okay, so we'll see in the next class with the new ideas. Bye students.